HTTPS. In this lecture, what we're going to talk about is how HTTPS works. And we talked about how HTTP work behind the scenes. We talk about how it is a request response system, protocol, and then how it sits on top of TCP, and then it leverages TCP as a streaming protocol to build its message-based protocol. But we need to encrypt it because we don't want anyone in the middle to sniff the requests and responses that we're sending, especially the ISPs, those nosy guys, right? So S was added on top of the HTTP using the protocol that is called TLS, or Transport Layer Security. And it sits, I don't like to use the OSI model anymore because it confuses things, but it's useful in certain cases. But the TLS, if I would to put it as a layer, it's going to be layer 6, layer 7. It's an application protocol, right before the application layer. You need to encrypt. Okay, and as a result, we need to do the encryption of whatever we receive from that library, from the node, from HTTP. So if we receive a request, we encrypt it. Then we pass it down to the kernel, TCP layer 4, right? And then they ship the bytes. So the kernel doesn't care if things are encrypted or not. The kernel just knows the IP and the port and then just sends bytes. The bytes happen to be encrypted. The kernel doesn't care, right? The Linux kernel doesn't care. The OS doesn't care. So let's talk about this. How does encryption work? What are we encrypting exactly? What are the different encryption algorithms? And then we're going to jump into Node. We're going to talk about certificates and authentication, things like that. It's going to be a long lecture. Sit tight. Enjoy. So HTTPS, still we have the hypertext transfer protocol, but the secure version. And that if you see a URL with HTTPS, obviously it means it's encrypted. It means anything between you and the first destination, let's say, not the final one necessarily, is encrypted. Right? That doesn't mean that if you're talking to an actual backend and the backend happened to use a CDN, then it's not end-to-end encryption per se, right? There is an encryption between you and Cloudflare, and Cloudflare decrypts the content in order to see it, to cache it, and then Cloudflare or the CDN turns around and then re-encrypts it and send it to the actual backend. So your encryption is only up to the whatever the front-end edge server that you're talking to, based on your the destination IP address. Does that make sense? So just watch out for that, because a lot of people think that since you're HTTPS you're completely encrypted. You're not, right? It depends how things are done, essentially, right? So the encryption is between here and here, and this is called, if you have a proxy or an API gateway, it has to decrypt. So it has to terminate TLS, as they say. Okay, so just watch out for that. So yeah, Node has support for HTTPS, both the client and the server. I need to say this because it's critical to understand the difference between HTTP clients and HTTP servers, and HTTPS clients and HTTPS servers, right? So there is a complete different work being done, and understanding what is being done really boils down to being a server or being a client, being the emitter of requests, receiver of responses, and being the emitter of responses and receivers of requests. Right? And as a result, you can implement TLS, you can implement protocols differently. And everything is on top of this TLS library. Let's talk about this. What is this exactly? So in order to talk about this, we're going to dive a little bit into what encryption really is. And I don't want you to, I don't want to bore you with the details, to be honest. I'll try to add the necessary details here. And that's, if you need to know anything about encryption, you need to know there are two types of encryptions. Symmetric and asymmetric encryption. That's the most important thing to understand. And symmetric encryptions are encryption that you use a key to encrypt the content, and you use the same key to decrypt the content. Okay, and that's why it's symmetric, because it's the same, right? Whatever key you used here, you're gonna use the same key to decrypt it at the other end, right? Well, the challenge with this, well, the good thing about it is it's absolutely fast. Symmetric encryption is fast because it uses simple CPU instructions to do the encrypt, as long as you have the key. And decryption is also fast, yeah? As long as you have the key. The problem is, the challenge is, how do you get the party to have the same key as you? Like if you own your own thing, let's say you have a key and you want to encrypt it so nobody swoops in on your stuff, that's nice, right? You can keep the key with you all the time, I don't know, in a wallet or somewhere, and you memorize this series of numbers, and then nobody can ever do anything with it, right? They can have the encrypted content, but they don't know what the key is. They don't know. I have absolutely no idea how to decrypt it, right? So you can come back with the same key as you, and then you're the only one who can decrypt it. That's fine. But if for communication, it becomes a challenge, because now you have to have two parties agree on the key. And that's where the challenge becomes, right? So that's where asymmetric encryption came into the picture. Let's have two keys. One that is public, and I'm going to use the red key here for public. That means like anybody can see it. And then one that is private that nobody can see, right? And the good thing about this is you can keep your private key and you can encrypt content and it goes both ways. You can encrypt content with the private key and only the public key can decrypt it. And you can encrypt content with the public key and only the private key can decrypt it, which is pretty cool. Now, how? If you're interested in the math, I'm not. I'm gonna link some. Just Google RSA, how RSA works. That's one of the algorithms that supports asymmetric encryption. But that's how it basically works. There's math genius behind asymmetric encryption, right? And there are like so many algorithms, that comes after that. But that's essentially it. You have two numbers. And keys are really just numbers, like large numbers, and they're like sizes, like 256-bit, 512-bit, 2048-bit, 4084, 4096-bit, and that's it. And they keep breaking. They keep using quantum CPU to break asymmetric encryption. So we always have to increase the size of the keys. Like RSA, I think 1024 is easily breakable. 2096 is a little bit easier, but that's why you have to have like 4000 and more to become harder to break, right? So anyway, like elliptic curve Diffie-Hellman comes into the picture. Anyway, regardless, what you need to know from all of this mumbo jumbo is asymmetric, you have two keys. Symmetric, you have one key, right? The same key encrypts and decrypts. Asymmetric, two keys. One key encrypts, one key decrypts, and you can flip them. And you can flip them to do certain interesting applications. We're gonna come to that, right? Just know these facts. That's it. We always want to encrypt with symmetric encryptions. That's the fact. Because symmetric encryption are amazing for large data because they're fast. But the problem is the challenge to exchanging this key to the other party, right? I mean, you can call them and give them the number, then you have to trust your phone company not to get that number. And you can just mail them, but you have to trust the mailing system. You can, I don't know, send it with what's hammam zarjan in English? Pigeon. What's the pigeons? The carrier pigeons. You can send it with carrier pigeons, and then But that's the challenge, right? But the problem with asymmetric encryption, the good thing about asymmetric encryption is like, hey, I can send the public key. Like anyone can have it. So the other parties do have my public key. I can keep my private key and I can do something, send it over. Nobody can encrypt it. Nobody can decrypt it except the ones who have them. With the public and private, it's pretty convenient. If I'm the owner of the public key, no, if I have your public key, I can send you a secret message. I can basically take the secret message, encrypt it with your public key, and I send you the encrypted message. And if you receive it, you are the only one who can actually decrypt that message. Even though everybody has the public key, they cannot use the same public key to decrypt it. You can only encrypt with it, right? So the private key, if you use it, you can see my message. So if I sent you something with your public key, then you can see it. And that's one way to do it, So, but the problem with asymmetric, it's expensive. It's very compute heavy to actually do to the public key encryption. That's why we don't use it for large data. It's just so slow, right? It's getting better, but symmetric is the way to go. So that's encryption in a nutshell. So here's the symmetric encryption, just more examples here. Assume both parties have the same key. This is the most difficult thing, right? Let's assume that. Let's talk more about symmetric encryption. So let's assume the blue guy has Bob, always like in the encryption for some reason, Bob and Alice, A and B, right? So this guy have the symmetric key, and Alice also have the symmetric key. Okay, so Bob, the blue guy, takes the plain text message and they encrypt it using a certain algorithm, and the message is nothing but bytes, right? So you use the number bytes with bytes. Usually it's a simple XOR. Sometimes it's more complicated than that. There's like, you can major in this stuff if you're interested. Like I took a course in cryptography back in 2001, long time ago. But yeah, there's like a chain. You can chain the blocks and to make it a little bit difficult to break. But yeah, you do this, and you get this message. This is the encrypted message. I made it yellow. So now if you send it, nobody in the middle sniffing this thing can actually make any sense of it. It's just a bunch of bytes. So yeah, nobody can do anything with it. So once I receive the message, when we receive the message, we take the encrypted message, we use the same key and the same algorithm. We have to match the algorithm because there are a lot of encryption algorithms as well. Symmetric encryption algorithms. You have to match it so that you have to send the encryption algorithm to the guy that you used, and they should have the key. And they apply this to the key, and then they get the plain text. So use the same key to decrypt. An example is AES. So that's a very popular example. And you usually see AES 128, which is the block size, because it's a block cipher, right? So we encrypt by blocks. So we take 128 and then we encrypt it. Poof, 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 poof. One block at a time. 128 bytes. So let's talk about public key and private key. The rules first. Here's the rule. By having the private key, just the private key, you can generate the matching public key. So even if you lost the public key, you're fine. You can always generate the public key from the private key, but you can never get the private key from you can never get the private key from the public key. That's impossible. Okay. Well, if you have all the compute in the world, you may be able to do it, but it's a very, 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 very difficult job. So that's one thing, and we're gonna do this. We're gonna show you how to do this, right? Using OpenSSL, which is a very popular library, open source SSL library. SSL is the old name for TLS, secure socket layer. So keep that in mind. So we're gonna encrypt with the public key now first. When we encrypt with public key, I can prove the authenticity of the receiver. So anyone can have this public key. You can safely share this red key. to anyone. Like, you can publish it, post it, and you can ask, hey, if you want me, this is my public key, and you can use it to encrypt a message and then post it to that guy, and that guy can take it and use their own private key and see what you send, and nobody on earth can know, right? Except if the private key is leaked, right? That's a different story. So you can encrypt the message with the public key, and only the owner of the private key, right? You can encrypt a message with the public key, and only the owner of the private key can decrypt it. This proves authenticity. I know that if I encrypt this message with this, I get this, and I send it over, and this is the encrypted thing. I use as the owner, I use the private key, and I apply this message, and I get the original text. It's an asymmetric cipher, right? Because it's the opposite. You use the opposite thing. And you can actually do the opposite. You can encrypt with the private key, right? And send it over. It's kind of, you might think it's pointless. Well, if you encrypt something with a private key, wouldn't anyone with the public key be able to decrypt it? Absolutely. Anyone. Even a hacker here can see what you send. So you don't use this for actually encryption, but for confidentiality. So let's say for digital signature, if you ever seen this, right? This is perfect. Let's say I produce a statement, right? I, Hussein Nasser, and I want to write some statement. I want to publish it outside, right? And everybody knows my public key. That is a trusted public key, right? You know that my public key is this. And I wrote a statement. I wrote a message. I published it publicly. So, all right. I posted a message, okay? And people say, no way, this guy said this. But can you prove it? Well, what I can do is like, hey, I actually wrote this. Here's the message, and I'm going to use my own private key to sign it. And I'm going to put this digital signature underneath it. And I give you this message. If to prove that I am the one who did this, you use my public key to verify it, and you decrypt the signature. They use a different word, not decrypt, but I like to use decrypt. Oh, sue me. Okay. So you decrypt the signature and you get back a valid message saying that, oh, this actually matches. Usually what you decrypt is the hash of the document, so that you matches that whatever this said in this document, the hash of it is actually inside the signature. So yes, Hussein actually said this. And this is very, very critical. Especially, we're going to use this all the time to sign messages, to prove that nobody has changed this. Because if someone has changed the message, the document, to say something else, let's say, then they have to re-sign it again, right? With their own private key, because they don't have my private key. So if they change something, they have to sign it again. Okay? Because the signature will not match the content, the hash. So what they do is like, if the hacker changed the message, and they won't be able to sign it again with their with my private key, because they don't have it. So everybody knows that, this message has been compromised, right? This document has been compromised because the signature doesn't match the content, right? So that's basically why we use digital signature here. Very critical. Encrypting. So you can use it both way. Private, you encrypt with the private key, right? Decrypt with the public key for confidentiality, for digital signatures. And you can do the reverse to prove the authenticity. We're going to use both, actually. Let's talk about the most important thing here. Certificates, you guys. You know what certificates are? It's a way to prove authenticity. You see, when you connect somewhere to a server, to a server, example.com, how do you know that whatever you're connected to is whatever you're connected to? You need some sort of authenticity. So we use public key communication all the time. Today, with HTTPS. And the key is this guy, the public key, right? So certificate is nothing but a metadata to carry the public key. That's it. Hey, if you want someone's public key, you don't ask for the public key, but you ask for the certificate instead, right? Because the certificate doesn't only contain public key, but other useful metadata. The version, the signature algorithm, the digital signature, we talked about that. The issuer name, right? Who issued this, the subject name, the owner of the certificate, the subject alternative name, which is the most important key title here, which is the site itself you're connected to. Like if I go to example.com, I'm expected to get back a certificate that has a subject alternative name, example.com, which matches the website. So yeah, subject alternative name is where the website saves, okay? So what do is here's what you do. You generate a pair of keys, private and public. You generate a private, and from the private, you're going to generate the public. And using both, you can generate a certificate. What you do is you put the public key in the certificate. That's all you already do. And you put the website name in the certificate. And then you sign the certificate. With what? With the private key. You don't put the private key inside the certificate. That defeats the purpose of the whole thing. Right? That defeats all purpose. You just sign it. And here's the digital signature, by the way. You get like the value of all the thing that signed by issuer's private. And that's it. You have a certificate. Meet X509. That's the standard for certificates today. That's X509. That's how we build certificates today. Okay? So that's the certificate. But certificates are more complicated than we think. You see, you can have a certificate that is first self-signed, i.e. the private key signing the certificate is the same as the public key is inside the certificate. If you have that, you're signing your own certificate, essentially, which is often not trusted. And these are called self-signed certificates. Right? If you sign your own certificate, which is, if I'm spinning my own server locally, I'm probably going to sign my own certificate. I can sign. The legitimate way of doing certificate publicly on the internet is to have other certificate authorities to use their private key to sign my certificate. This is trusted because those certificate authorities which they have a certificate, they themselves are also signed by other certificate authorities, and those are signed by other certificate authorities, and the chain goes for a long time. It could be 1, could be 3, could be 1, could be 2, 5 chains deep, but until at the end you must get into something called a root certificate. Ultimately you find a root cert. And the root cert is a self-signed certificate. Hussein, you just said self-signed certificate are not trusted. Doesn't mean every single root certificate is not trusted. Well, here's the exception we're making. The certificates that are self-signed and they are root, they are essentially trusted by everybody on the internet. There are maybe 13 of them or so. And here's the thing. You can check them for yourself. Those are stored in your computer. When you install your operating system, it comes with something called a certificate store, which has a list of root certificate, which has a list of certificate authorities, and it has like a big list of all this stuff. So when we do verification, I receive often just this guy, the leaf certificate. So what I do is like I look up, okay, this is your certificate name, but who, and this is your public key, but who signed you? Well, the issuer, where is the issuer? Issuer name, who issued this certificate, The issuer is CA. Okay, so you look up CA in your store. Now, if you find CA in your store, then you look up who signed CA. Because someone else has signed CA. Who's signed it? It's the root. And you look up root in your store and say, oh, I found it and it's trusted. So A.com is trustworthy because root signed the certificate authority and the certificate authority also signed A.com. So we're good. This is a trusted certificate. That's how you trust the certificate. Okay, that's the chain. That's how it's happened. Sometimes when you send from the server, you can send this full chain. It literally is called full chain, and it's large when you do that, because sometimes clients don't have the intermediary certificate authorities in their certificate store, right? So you need to send the full chain, right? In certain situation. And if you do, yes, it's large, but you get to support more clients essentially. Yeah? And in that particular case, you look up A.com and you find that A.com was signed by CA.com. You don't trust that. You just say, hey, okay, I trust that, yes, you say CA.com signed your public key with their private key. Sure, but who signed CA? You still didn't tell me. Well, root signed CA. And you look up root and say, okay, root signed, yeah, but I don't trust root yet. Then you take the root and say, okay, let me look up in my search store. You always look up in your search store. And you say, all right, I found root, trusted. Nope, I didn't find root, rejected. And you can disable this whole behavior by doing -- verify false, right? And literally you can disable it in Node. We're going to talk about all of that, so how to disable in Node and things like that, right? But yeah, it's certificates and chains is so interesting. There's so much more you can dive into this. And I'm sure you have more questions. We can have discussion in the Q&A section about that. But yeah, essentially they're trusted by everyone whoever has the cert store. Sometimes it becomes like, oh, some browsers don't even trust the operating system's certificate stores. So they have their own certificate stores. They look up into their own certificate stores. They don't trust the OS. Sometimes you get shipped a laptop from China or Kazakhstan where there is a special operating system with some nasty root certificate installed in it. Why? Because when you make a request, the ISP that you're connecting to, if it's malicious, it can intercept the traffic and pretend to be google.com. And how does it do that? Is by generating a certificate that claims to be google.com signed by their root certificate. And when they do that, you as the malicious computer receiver, you will look up that google.com certificate, which is not correct, but you don't know, right? You look up who signed it. Oh, CA signed it. Who signed CA? Root Kazakhstan. They literally did this, the government of Kazakhstan. That's why I give them as an example. And then, okay, who signed this? Well, okay, root Kazakhstan, KZ, whatever. I look KZ in my store and oh, it's there. Trusted. Let it in. And just like that, all your stuff has been decrypted essentially. You were man in the middle, right? Completely, right? Anyway, let's move on. Okay, here's the certificate verification. Whatever I just explained here is all here, right? So here's the A.com. The issuer is CA. The public key is APB, A public key. And then this is the signature. It's signed by CA private key, right? It's signed. It's not the private key itself, but it's signed by this guy, right? So you can see that this is, so you look it up and it find this. And of course you don't trust this. So you find, okay, who signed you? Okay, root trust find you, look it up. So it's all look up, right? And then you find this. And sometimes the chains get complicated. Sometimes you can do cross chaining, like another root, right, can sign two. Like one certificate can be signed by two roots, right? On this one, this like this. And there was like bugs with this because some client verification were only going one line, you know, like whatever is this depth first, whatever, not breadth first, just depth first, right? It will go there and then we'll find something, and when this expires, it will fail. Although there was like another cross-signed route that is valid, so they really need to go this and then do a breadth search and find all the other chains. You know, nothing is free, you guys. Everything is expensive. Everything there is. You can be an engineer in any of these areas. You know, it's unlimited. Hussein, when are you going to talk about Node? Soon. Don't worry. TLS. We still did TLS. We did. Guys, trust me. Trust me, bro. Just wait. TLS security. Encrypt using the same key both client server. That's how TLS work. We use symmetric keys for TLS, right? And these are called session keys, right? But the problem is we face is we need to exchange the key, because I am talking to google.com or example.com or husseinnasser.com. I don't know any of these sites. I talk to new websites every day. So I don't know every single public key out there, right? I don't know the symmetric keys. We're not exchanging keys. So we exchange keys every session. With every new connection, with every TLS session, which sits on top of a TCP connection, a TLS session sits on top of it. It's a virtual thing that has these keys and all the keys and symmetric keys and all that stuff, right? Algorithms and encryption ciphers. Then what we need is we use public key encryption to exchange the keys. Yes, it's very nice. We share the certificate for authentication. Why? Because here's the thing. If I just use the public key, I can see a public key out there and I use it. But how do you know that this public key actually belongs to Hussein, or actually belong to Google, or actually belong to Netlify? You don't. So you need certificate for authentication. So you don't share public key, you know, willy-nilly out there. You need a certificate wrapper, right? And the certificate is chain, really. You need the whole chain, which is then signed by this. And you can look it up online. You know, even if you just receive the Leaf certificate, you can look up the issuer online and find out all of this stuff. I'm gonna go through TLS 1.2, but only one encryption scheme, one exchange scheme. That is all. That's no longer being used. Okay, but this is just an example. 1.2 or earlier, this is RSA specific, right? We used to do this. Okay. TLS 1.2 is safe, but if it's that particular option is not, you know, because it has like tons of options. This option is no longer viable, right? But I'm explaining it to you as an example. Yeah, I mean, you can use it. It's not a big deal, but something happened in 2014, something called Heartbleed that caused the problem. And I'm gonna talk about all of that stuff. Don't worry, right? I know it's a Node.js course, but yes, don't worry. We'll get to the coding part. Don't worry, guys. Client hello. This is how you do it. You do a client hello. So you establish the TCP handshake already, but then you do a client hello. And then the server has the public key and has the private key. Okay. Remember, we want to exchange keys here. Okay. So what we do is we do a client hello, and the server respond back with the certificate, which has the public key, right? So X509, okay? We get back an X509, which has the public key, because we cannot just send me the public key, because that's easily any hacker can intercept this and send their own public key, and we will be gonna be in a problem. We don't want that, right? So we want an actual certificate. Why? Because that's the only way today to verify anything, right? So because it's a chain of chain until you get the real. So we get that. We get the public key. Now I trust the public key because I did the certificate verification that we talked about, right? Went all the way, checked my client. Yes, that public key, that certificate is valid. I trust it. What do we do next? The client generates the symmetric key, the golden key. Then what do we do? You encrypt the symmetric key with the public key that belongs to the server, and you send it. And this is encrypted now, okay? And you just send it over. Go change cipher fin. Let's go. And now the server receives it. Anybody in the middle can read this, but they cannot find the key because they don't have the private key. You need the private key to decrypt that. Remember, that's how asymmetric. That's the power of asymmetric encryption. Once you encrypted the public key, nobody ever can find it, as long as you know this is the public key that actually belongs to the server, and that's where we need certificates, right? Without it, the whole thing is pointless. I get it. I decrypt it. What do you think about the animations? That's the only animation you're gonna get in this slides. Sorry. We decrypt it. We found it. And that's how you exchange. The old days. Yeah, well, there's a better way to do it. All right. Now both of us have the private key. The symmetric key. Now we can just change the cipher and then start encryption. Now the client, this tells the client that, hey, I'm done. So how many did we do? We did 2 handshakes, 2 round trips to do this work, right? But then the client managed to encrypt it. They encrypt the content and send it over. And then the server, what does the server do? Does the same thing, decrypts it, and we talked about that, right? Once we have the symmetric key, this is easy. We use the symmetric key to decrypt, and then Node gets it and decrypt it, right? Of course, and then it goes into the request object and all that jazz. And same thing with the client, right? Okay, what's wrong with this then, Hussein? What's wrong with this? Well, you need my reaction. My reaction for this. Well, the problem with this is the following. It is not perfectly forward. What does that mean? You see, true that the attacker doesn't have the private key of the server, but it can record this entire conversation. Encrypted might it be, right? Encrypted. And let's say the attacker had faith, because he had faith, and it just sat down and recorded every possible communication. He sat in the middle, he intercepted the router, and then he just recorded any communication to example.com, that server, and he saw tons of encrypted symmetric keys, and he just recorded them. He just stored them. I don't know why I say he, but they just stored them, right? And then he just kept all of this in a storage. One day, I know I cannot decrypt this, but one day, something bad happens. The private key gets leaked. Someone leaks this guy. It's out in the public. There was an attack called Heartbleed back in 2014 that literally you can send a payload to the server and it will reply back with whatever in the memory. You can say, hey, give me anything with 1,000 bytes, and it will just read anything in the memory and just print it back to you as a response. So people got everything in memory, including the private key, which happens to be, because where it is, of course it's in memory, right? So just the private keys were leaked and very nasty things like that. And then, so you got the private key. After a year, you have gigabytes of recorded conversations that are encrypted. what do you do? What do you do? What do you do? You just go and you take this guy and you apply the private key that is leaked, and then all of a sudden you have the symmetric key. Well, this has been encrypted with this symmetric key, so decrypt, decrypt. Just like that, you decrypted every single possible communication in the past, right? Because another session might use another symmetric key, but that's fine because they are using the same private key to encrypt it. So you got it, and that's why that's the problem with the. It's not perfectly forward. People didn't like that, so people invented a new method. Diffie-Hellman solves this. So what we needed to do is we don't send the symmetric key at all in the communication. We generate it using we break it down and generate it on two parties, and this is how Diffie-Hellman does it. Let's do the math here. So here's how they do it. It's a very interesting thing. So the key is like, let's not share the symmetric key, right? But let's share parameters enough to generate it. So that's what we're going to do. We're going to generate just enough parameters to generate it. That's it. That's the key here. And in that particular case, because everything is a number at the end of the day, they will be able to generate the same exact number using math. Let's do it. So party 1 generates X. Here's the algorithm. You generate X, blue and pink is private. Red, G and N are public. So the client generates G and N, and these are public, random, and they have to be prime, and they have to be large, right? And now what they do is like, hey, what you do is you send this to Y. Anyone can sniff it, that's fine. It's just G and N. These are two numbers. You might say, we'll come to that. We'll come to that. Don't worry. So we're sending G and N. So now both guys have G and N. So this guy has G and N and this guy has G and N. And here's what we do. Party 1, this guy, takes G and they raise it to the power of X and they do a modulo of N. So this is what you get. G to the power of X modulo N. G to the power of X modulo N. And they send this. Knowing this number, you cannot get X. Like, try it. Take a large number, raise it to another large number, and do a modulo N, which is also large. You're going to get a range between 0 and N minus 1, right? And knowing 0 and N minus 1 won't give you X. It's very hard to break that. So now this becomes a public value that you send. Boop, you send it to the other party. And this guy does the same thing. Y does the exact same thing, but with Y. So now both guys will have G. This guy will have G to the power Y mod N. And this guy will have G to the power X mod N as a value. But this guy has Y. So you raise this to their Y because X does not have Y and Y does not have X. So this guy take this value and raise it to the power Y, and you get this because of math, because that's how math works. If you do X to the power Y is the same thing as X to the power X times Y, right? Modulo N. Modulo N doesn't change anything. You get this one. And then this is exactly the opposite, because this guy has G to the power Y modulo N. It doesn't have Y, but they do have X. They raise it to the power X, and you get this. And they are the same number. They got the same number without sharing the key. They shared enough information to generate it, but anyone in the middle, if you are an attacker, you got this, you got this, you got G and N, but it's impossible, near to impossible to get X or Y or even this value. And that's basically how Diffie-Hellman works. We still have more problems, you guys. Man in the middle. We solve one thing, but we have another problem. That these keys, yes, they cannot be broken, but they can be changed, right? So let's say X will send their public value, and someone in the middle called Z, the attacker, will capture it and will keep it here, right? They will generate their own private key called Z. And then they will intercept Y, but then they're going to delete it. They're going to remove it. But then they're going to send their own parameter, G to the power Z modulo N. They're going to send it to X instead. So X, thinking that they are talking to Y, they're going to get this instead. And they're going to raise it to power X. And then they're going to get G to power XZ modulo N, which is the attacker's version of this. And then, of course, the attacker will take this and raise it to the power Z. And what do they have? They have the same thing. So now, we just broke the encryption, right? The attacker was able to break the encryption without actually breaking, needed to know why. And that's the problem, because everything is just numbers, right? So how do we solve this? That's easy. Sign. We just sign. So this is another reason why certificates are the most important thing, you guys. That's why the certificates are the most important thing. Without certificate, everything breaks. Everything breaks, right? Okay, let's do the certificate. So generate X. That's just exactly what we just talked about, but in a prettier way. So this is what we do. All right. So with certificate, everything is solved, right? So I send my parameter G to the power X modulo N. I take it, I get the symmetric key, right? Of course, you pass this number, the seed, into an algorithm that gets you that. It's not like straightforward, right? But once you get the number, it's basically easy, right? So now the server has the key already. That's it. TLS 1.3 is much faster because we just send something, everything we need right there, right? In one shot. And then immediately the server has the symmetric key. But now we need to let the client know that about G to the power Y N. And we really need to sign it with our private key, right? We need to sign it with the private key. That proves we need to sign it with our private key such that the whole thing is signed with the public key, including the certificate, including this. Entire message is signed with this. We don't send the private key. We just sign it, okay? We're not sending this guy. We're just signing it. So if I receive it, now I trust it. Because first of all, I take the public key. First of all, I do the certificate verification. Is the certificate to be trusted? Yes. Let me go through the chain. Up. Root. I found the root in my certificate store. Good. Now the public key is trustable. Let's take that public key and let's sign let's decrypt this signature. Is it really that guy that did this? Yes, that's the guy who did it. I trust him because the public key is there, and I trust the public key because the certificate is trusted, and I trust the certificate because it's my store. And if it's not my store, I'm screwed anyway, right? Yeah, again, everything, you're screwed if you don't have in the store, right? And then I generate, of course, I do that. Yes, trustable. I encrypt. I have this key, and that's it. We verify everything. We talked about that, and then we encrypt. There's more to TLS, you guys. This is we just scratched the surface, isn't it? We barely scratched the surface, I swear. We just scratched the surface. We didn't do anything with TLS. There is a lot of extensions, ALPN, SNI, signature algorithm, key generation algorithm. There's a size to the key. There's digital signature algorithm. Client-side certificates, another thing if you want to do MTLS, mutual TLS. But yeah, it's a word by itself, and it's impossible to cover all of this in one course. So now let's talk about non-HTTPS, right? How long do we have? Almost done. Non-HTTPS, now that we understand, guys, you cannot skip all of this you cannot just pass in certificate and just, oh, now I have it. Now you understand how things work. So no, it requires a certificate, the public key, and a private key. You need both. The rest is the same, right? It's just like, it's identical. Everything is the same, except we get additional cost of encryption and all this certificate verification and all that stuff, right? So we're going to generate a private key and a certificate with OpenSSL. That's our beautiful library to generate that. And to generate it, you do OpenSSL gen RSA. I'm going to use RSA. I'm going to use this much key size. You can increase it if you want, but this is just a sample. I'm going to output a private key.pam. That's the output for private keys. .pam. Okay. So I'm generating a private key. And then we're going to generate an X509. So using OpenSSL, we're going to request a new 509. You have to give me the key. Using the key, I will generate the public key, and I will generate you just the public key and also the certificate. And I'm going to make it valid for 365 days. And it's going to ask you some question to fill up the 509 fields. And the most important thing is just the subject name, really. That's the most important thing. But you can fill it up, really. And here's an example server. With that, we use read file sync. You can change it, but it is just an example. As I'm reading, I'm reading this from the disk, the private key, very critical. Without it, we cannot do anything. And the certificate, which is the full chain, really, which includes anything that comes on top of it, right? You can have like let's encrypt also, sign your own stuff. Maybe we'll do an example. We'll see. But yeah, you create a server normally. This is how you do an HTTPS. You listen on any port you want. The rest is identical. The only difference is that really you're referencing HTTPS as opposed to HTTP. And here, the request is decrypted before we even get here. And that's the trick here, right? So when we got here, we already ran through all the decryption and the OpenSSL and all that logic. Everything is done. And here's the same thing, but for the client side. For the client, you don't really need to do any certificates or anything, right? Because the server is responsible for the certificate, not you. But there is an option to do client-side certificate, right? If you want. Because technically what we only try to verify servers. We don't really try to verify clients. Some servers do try to verify their clients, but you can, essentially, if you want to do that. Everything is the same. The only difference is HTTPS. Summary. We did encryptions. We talked about the encryption. We talked about TLS. We talked about certificates. We talked about node HTTPS, how it was working, essentially. And then let's go through exercises. We're going to do a raw HTTPS request, and then we're going to generate our own certificate and public key. Let's go, you guys. What do we have? We have 3 things to do this. Let's do this. Here's how you do an HTTPS request. You reference the HTTPS library, and then you do HTTPS.request, and then you just specify the HTTPS. Now, I mean, Fetch and Axios can do both, but that particular, if you do just HTTP, you cannot do HTTPS because there's more logic to it. And I'm glad there are 2 libraries for that, just to let you know that it's not something simple, right? There is work that being gone into these things, right? So let's run this. Node 16160, really simple things. It's slightly slower. Nothing is different. The only difference is like it's encrypted behind the scenes, you know? And there is a lot of work being done here, essentially. And then if we were to do like here, the same thing, we do a curl -v https example.com, you will see whatever we talked about, it's right here. Curl show you everything. It tells you all the IPs, then the server side, TLS out, I sent the client hello, we got the server hello, we exchanged, we got the encrypted extensions, the certificate, the most important thing, the certificate verification signed by the private key, and then all of that other stuff, what algorithm we used, what public key encryption, and the ALPN. We did HTTP2 in this particular case, and then all of everything is just laid down there. So let's do a server. Server is the most interesting thing, right? To do a server, we really need to generate the private key and the certificate, right? So I already did this, and I have this for you here to generate it, but you can just run these commands and that will generate the private key. And this, using that, once you have the private key, you can generate the private, the public key and the certificate. And when you do that, you will be asked a few questions. Let's go ahead and do that. Sure. Then let's do cd16 HTTP. Let's delete all the PIMs. Sure. Gotta delete everything. So let's go ahead and generate. You should have OpenSSL installed on your machine, because I can memorize this stuff, to be honest. Out private dash key.pm. Let's actually increase it, 4096. Right, more secure. And now, just like that, I had the .ignore to not push PM. For obvious reasons, you cannot push private keys to the GitHub, right? Goes without saying, I think. So now let's generate a certificate OpenSSL RIC new dash x509 dash key. Just pass it the private key that I just generated, certificate.pam, and then I want to generate. I want it to expire days, 100 days, sure. And then it'll ask you, what is your country name? US. What is the state? CEA. What is the locality name? Manama. I'm just making things up. This more. Home. You can fit. This is the most important thing. The name, right? The fully qualified name. Dot. And you can just put your website here. In this case, just localhost. We don't really care. Email address. And that's it. Just like that, we have certificate and then. Now, you need to read that private key as the key and the cert as the certificate. And that's it. You pass this options to the create server, and then you have yourself, my friend, a node server this name HTTPS running on 8443. So if you're gonna ever do HTTP2, you have to have an HTTPS server, and that's how you basically spin up an HTTPS server. So curl HTTPS localhost. Where's the other one? Localhost 8443. That's the port I'm listening to. And you can see that I got an error. Why? Because curl doesn't trust me, bro. Curl doesn't trust me. Two solutions to this. You can do dash verify false. Sorry, is it verify? I can't forget. Sorry, dash insecure. And you say, hello HTTPS. Or you can go to your certificate store and you physically take this guy and you store it in your certificate store. And you ask Node.js, do I have that example? I think I do. Oh, this is just, I don't think I do. Maybe I did. I could swear I did this at some point. But yeah, you can have Node trust that certificate by supplying in the request side. I think maybe I did it in another course. I can't remember, another lecture. Yes, or you can add it to the certificate store essentially, and that it will be trusted, right, by whomever using the certificate store of the OS, right? And you can add it. I think in Mac is different, and in Linux different, Windows is different. But you just import that certificate into your operating system store, or you can have, if you want Node to trust it, then you can add the certificate itself into Node and says, hey, Node, if you ever get this certificate, trust it, bro. Okay. And finally, same exact test that we did for the performance for the agent, but now it's an HTTPS agent and identical. But you can see that's a little bit, it's going to be a little bit slower to run these tests. Look at that. It's every single request we send has a little bit more work to do, which is the encryption part. But let's increase the number of sockets. Faster. But yeah, guys, that was a long lecture talking about certificates, encryption, and we can spend really 2 hours on this thing. But yeah, I thought I'll talk about this thing. I hope you enjoyed this lecture. I hope you give it some time and watch it again and just reflect on the amount of work that is happening on TLS. I know it's a much. I know it's a lot. I know, and most of you might not be interested in this stuff, but just having it at the back of your head as just that. Hey, when I do an HTTPS stuff, more work happens behind the scenes, and we'll get to that. We'll do Wireshark. We'll see what the cost is, because now when we do connections, there is TLS happens after that, which is another handshake. More work. More work means performance. More cost means performance. I'm gonna see you in the next lecture. You guys stay awesome.